Hi Year 12. This is the third video for the solutions of the 2022 Extension 2 HSC paper. And in this video we're going to look at questions 14 to 16. 14a. The two non-parallel vectors u and v satisfy this equation. For some real numbers lambda and mu, show that lambda equals mu equals 0. So we're going to start with that equation. So lambda u, I'm going to use this notation because I don't like the other one, is equal to 0, and this means that lambda u will equal negative mu v, and u will equal negative mu on lambda v, which means that u and v would have to be parallel, but it tells us that they are not parallel. So that means either mu is equal to 0 or lambda is equal to 0. Now we need to prove that they're both equal to 0. So let's suppose that mu is equal to 0. So that means that this vector here, coming from here, would be equal to the 0 vector. But that is not true because neither of these vectors are 0. So therefore mu has to equal 0 and lambda has to equal 0. Part 2. The two non-parallel vectors u and v satisfy this equation for some real numbers lambda 1, lambda 2, mu 1, mu 2. Using part 1 or otherwise show that lambda 1 equals lambda 2 and mu 1 equals mu 2. So starting with this and just rearranging it slightly, we're going to have lambda 1 take lambda 2 multiplied by u plus mu 1 take mu 2 multiplied by v is going to be equal to 0. And from part 1, we know that lambda 1 minus lambda 2 is equal to 0, and mu 1 take mu 2 is equal to 0. Therefore, lambda 1 equals lambda 2, and mu 1 equals mu 2. The diagram below shows the tetrahedron with vertices A, B, C, and S. The point K is defined by this, as shown in the diagram. The point L is the point of intersection of the straight lines SK and BC. Part 3, using part 2 or otherwise determine the position of L by showing that this is true. Okay, so we're going to start by saying, well, SL must be equal to some proportion, let's call it alpha, of SK. And so we know SK is equal to this, so this would be equal to alpha on 4 SB plus alpha on 3 SC. Now we also know that BL is equal to some proportion of BC. So that's along here. And I can rewrite BC as BS plus SC, or more importantly, because we want SB, so beta negative SB plus SC. Okay, now this is all very well, but what we really want is two equations for SL in terms of SB and SC. So this isn't going to cut it. We need to do some more work. Now BL, and it's here, is equal to BS plus SL, or in other words, negative SB plus SL. So I'm going to make SL the subject. It's equal to BL plus SB. Now let's substitute in this one here. That's beta negative SB plus SC plus SB. And collecting like terms, we've got 1 minus beta of SB plus beta SC. And that gives us our two equations. Here's the first one, and here's the second one. So we can say that alpha on 4 is equal to 1 minus beta, and alpha on 3 is equal to beta. Now I want to solve for beta, so I'm going to make alpha the subject here, and then substitute it in. So we're going to get 3 beta on 4 is equal to 1 minus beta, which is going to give us 7 beta on 4 is equal to 1, therefore beta is equal to 4/7. Part 4, the point P is defined by this equation here. Does P lie on the line AL? What we'd really like is this, AP is equal to some proportion of AL. Now we already have an equation for AP, let's work out one for AL. So AL is equal to AB plus BL, which is equal to AB plus, from the previous question, 4/7 of BC, which is equal to AB. So I'm trying to match these, ABs and ACs, plus 4/7, let's rewrite BC as BA plus AC, which of course is equal to AB plus 4/7 of negative AB plus AC, which is equal to 1 take 4/7 is 3/7 of AB plus 4/7 of AC. Okay, we know that AP is equal to negative 6AB minus 8AC. Let's factorise negative 2 out. This is 3AB plus 4AC. Close, aren't we? Let's times by 7 on 7 gives us a negative 14. 3/7 of AB plus 4/7 of AC. So it's equal to negative 14 AL. So because it contains the same point, point A, and we've proven that they are parallel to one another, P does lie on AL. 14b, let Jn equal the integral between 0 and 1 of x to the power of n e to the negative x dx. N is a non-negative integer. Show J0 is equal to 1 minus 1 on e. Nice easy question for question 14. This is x to the 0, e to the negative x dx is equal to, that's 1. And this integral is negative e to the negative x in between 0 and 1 is equal to negative e to the negative 1, take away negative e to the 0, which is 1 minus 1 on e. Part 2, show that Jn is less than or equal to 1 on n plus 1. Now, a bit of a tricky question, particularly under the time pressure of an exam. My initial thought was, I don't really know what this graph looks like. I don't know. And I really wanted it to be like a Riemann sum sort of question where this area between 0 and 1 was going to be less than the rectangle around it, and this would be n plus 1, but it just really didn't work. And the clue to this was to realise that x to the n is always greater than or equal to x to the n e to the negative x for x is greater than or equal to 0, because this is a fraction. Now that's Jn there, so it means Jn is always going to be less than or equal to the integral between 0 and 1 of x to the n dx. And this, of course, is where we're going to get our n plus 1 from, in between 0 and 1. And substituting in, we're going to get 1 over n plus 1 take away 0. And that's the answer. Part 3, show that Jn is equal to Jn minus 1 take away 1 on e for n is greater than or equal to 1. Now this is a really good example of good exam technique. If we can do part 2, this is a relatively easy question just involving integration by parts. So skip part 2 and move on to part 3. Alright, so we know that Jn is equal to the integral between 0 and 1 of x to the power of n e to the negative x dx. We are going to make this equal to u so that when we differentiate it, it becomes x to the n minus 1, which we can see here. So this will be u is x to the n, v dashed is equal to e to the negative x. So u dashed is equal to nx n minus 1, and v is equal to negative e to the negative x. Right, so this is equal to u times v. In between 0 and 1, take away the integral between 0 and 1 of u dashed v. So nx to the n minus 1 times negative e to the negative x dx is equal to, substituting in, we get negative 1 e to the negative 1, take away, plus, put the 0 in gives us 0, I'm going to join those negatives together, plus bring the n outside, e to the negative x, x to the n minus 1 dx is equal to negative 1 on e plus n I n minus 1. And we've probably got it at that point. We do n I n minus 1 take away 1 on e. Part 4, using parts 1 and 3, show by mathematical induction or otherwise that for all n greater than or equal to 0, this is true. So let's start with n is equal to 0. So j naught will equal 0 factorial, take away 0 factorial on e, multiplied by the sum from r is equal to 0 up to 0 of 1 on r factorial. Now we need to know that 0 factorial is equal to 1. So this is equal to 1, take away 1 on e, and this thing here, that's equal to 1. So j naught is equal to 1 minus 1 on e. Therefore, it is true for n equals 0. Next, we're going to assume it's true for n is equal to k. In other words, jk is equal to k factorial. Take away k factorial on e. Sum from r is equal to 0 up to k of 1 over r factorial. And now we need to prove it true for n is equal to k plus 1. So we are required to prove that jk plus 1 is equal to k plus 1 factorial minus k plus 1 factorial on e, sum r is equal to 0 up to k plus 1 of 1 on r factorial. Using part 3 and rewriting, we've got jk plus 1 is equal to k plus 1, jk minus 1 on e, and now using our assumption, substituting it in, we get k plus 1, and we've got k factorial minus k factorial on e, sum from r is equal to 0 up to k of 1 on r factorial, take away 1 on e, and expanding through there we're going to get k plus 1 factorial, take away k plus 1 factorial on e, sum from r is equal to 0 up to k of 1 on r factorial, take away 1 on e. So let's have a look what we've got. We've got the k plus 1 factorial, take away k plus 1 factorial on e. What we don't have is this upper limit of k plus 1. So what I'm going to do is make it and then subtract and adjust. So minus k plus 1 factorial on e. So what I want here is r is equal to 0, k plus 1, 1 on r factorial. And I need a minus 1 on e out here. Now, what I have done there is included a 1 over k plus 1 factorial. So now I'm going to subtract it. Does that make sense? Hopefully it does. So expanding that out, we're going to get this, take away k plus 1 factorial on e, sum from r is equal to 0 to k plus 1 of 1 on r factorial plus k plus 1 factorial on e times 1 on k plus 1 factorial, take away 1 on e, which gives us 1 on e, take away 1 on e, which of course is equal to k plus 1 factorial minus k plus 1 factorial over e, sum from r equals 0 to k plus 1 of 1 on r factorial as required. Therefore, true for n is equal to k plus 1 by the process of mathematical induction, true for all n. Part 5, using parts 2 and 4, prove this. Alright, so we're going to start by using part 4, which says this. So jn, which is this integral 0 to 1, x to the n, e to the negative x dx, is going to be equal to n factorial, take away n factorial on e, sum from r is equal to 0 to n of 1 minus r factorial. Now I'm going to take this n factorial over to the left-hand side, like this. Is equal to 1 take away 1 on e, summation of r is equal to 0 to n of 1 on r factorial. And I'm going to take the limits of both sides. So the limit as n approaches infinity of 1 over n factorial integral between 0 and 1 of x to the n e to the negative x dx is equal to the limit as n approaches infinity of 1 minus 1 on e summation of r is equal to 0 up to n 1 on r factorial. Now the limit as n approaches infinity of 1 on n factorial is 0, and this left-hand side is going to be equal to 0 provided the limit as n approaches infinity of this integral is not infinity, and we know its upper limit is 1 over n plus 1. So left-hand side is equal to 0. Is equal to the limit as n approaches infinity of 1 is 1, take away 1 on e, and then we have the limit as n approaches infinity of sum of r equals 0 up to n of 1 over r factorial, which gives us 0 is equal to 1 minus 1 on e, the limit as n approaches infinity of the sum of r equals 0 up to n 1 over r factorial. And so 1 is equal to 1 on e times the limit as n approaches infinity of this sum. Therefore, e is equal to the limit as n approaches infinity, sum from r equals 0 up to n of 1 on r factorial. Okay, 15a. I'm not going to read all of this because mostly it is just describing the diagram. This is important. The machine moves vertically upward at a constant velocity, which means acceleration will be equal to 0. And this part here, let the tension in the first rope be T1 newtons, and the tension in the second rope be T2 newtons. The mass of the machine is capital M kilograms. Acceleration due to gravity is g meters per second squared. Part 1, by considering horizontal and vertical components of the forces at P, show this equation. So let's start off with the horizontal system. And in this case, we're going to have this part here and this part here, and they're going to be equal. So T2 cos phi will equal T1 cos theta. And then vertically, we're going to have 3 parts because we've got this tension, this weight, and this tension. So we're going to have mg plus T2 sine phi will equal T1 sine theta. Now you can see from the equation that we want to eliminate T2, so let's make T1 the subject of that first equation. So T2 cos phi over cos theta. Now let's substitute it into the second equation. mg plus T2 sine phi is equal to T2 cos phi on cos theta times sine theta. Where are we going with this? I can see I've got that tan there. So mg plus T2 sine phi is equal to T2 cos phi tan theta. And now let's divide everything by T2 cos phi. That will give us mg over T2 cos phi plus this one divided by this is tan phi, and this one divided by this, the T2's cancel out, the cos's cancel out, we've got tan theta. And that's what we need. Part 2. Hence or otherwise show that the point P cannot be lifted to a position 2h on 3 meters above the floor. So we want h minus L to be less than or equal to 2h on 3, which is this distance here. Okay, we're going to start here. Now tan theta is equal to L on D, and tan phi is equal to, this distance here is h minus L, the h minus L on 2D, plus mg on, now this part here, T2 cos phi is equal to T2 times 2D on T2, so it's equal to 2D. All right, we can divide everything, or multiply everything by D and get rid of those. And now multiplying everything by 2, we get 2L is equal to H minus L plus mg, and I'm going to make mg the subject, which is 3L minus H. Now we know mg has to be greater than or equal to 0, and so 3L is greater than or equal to H, L is greater than or equal to H on 3, so that's that part here, which kind of implies that H minus L will have to be less than or equal to 2H on 3. 15b. The diagram shows two positions of a single piston in the cylinder chamber of a motorcycle. Piston moves vertically in simple harmonic motion between a maximum height of 0.17 meters and a minimum of 0.05 meters. The mass of the piston is 0.8 kilograms and it completes 40 cycles per second. What is the resultant force of the piston in newtons that produces the maximum acceleration of the piston? Give your answer correct to the nearest newton. Okay, so if it's simple harmonic motion, we can see it's got a different center. In fact, let's find out that center first of all. So our max is equal to 0.17 and our min is equal to 0.05. So 0.17 take away 0.05 is 0.12, and then divide that by 2 gives me 0.06, which of course is the amplitude. And then to find that center of motion, you can either subtract that from the maximum or add it to the minimum. So it's going to be 0.05 plus 0.06, which is 1.1. So we're going to have acceleration is equal to negative n squared x minus c, the center of motion, x minus 1.1. And now we need to work out n. Now we're told that the piston completes 40 cycles per second. That's actually the frequency. And frequency is equal to 1 over the period. And so our period is 1 over 40. Now we know that the period is equal to 2 pi on n, because this is either going to be a sine or a cos curve, and the period of sine and cos is 2 pi. And solving for n is equal to 80 pi. So we have that a is equal to negative 80 pi all squared, x minus 1.1. Now we're looking for maximum acceleration, and that's going to occur when this is equal to the least it can be. So we want x to be 0.05. So a max is going to happen here. 0.05 take away 1.1, which is equal to 0.06 times 80 pi all squared. Now we want the force when the acceleration is maximum, so F is equal to ma. Mass is 0.8 times 0.06, 80 pi all squared, and into the calculator and to the nearest newton we get 3032 newtons. 15c. Using the substitution x equals tan squared theta, evaluate that integral. So we'll start with x is equal to tan squared theta, and dx d theta is equal to 2 tan theta, and then multiply by the derivative of tan theta, which is sec squared theta. Let's do the limits. When x is equal to 0, theta is equal to 0. And when x is equal to 1, we have 1 is equal to tan squared theta. So theta is going to be equal to plus or minus pi on 4. But we can see from this that we're in the first quadrant there. So theta is going to be equal to pi on 4. Okay, let's substitute in. Equals integral between 0 and pi on 4 of inverse sine of the square root of x is tan squared theta over 1 plus tan squared theta times dx, which is 2 tan theta sec squared theta d theta. How awful. Equals integral between 0 and pi on 4 of inverse sine. We've got tan squared theta over 1 plus tan squared theta is sec squared theta and then I've got 2 tan theta sec squared theta d theta equals integral between 0 and pi on 4 of inverse sine. What do we got here? Tan is sine squared theta over cos squared theta, and sec squared theta is 1 over cos, so that's times by cos squared theta. Oh, that's nice, that cancels out. Times 2 tan theta sec squared theta d theta equals the integral between 0 and pi on 4. Now, inverse sine of sine theta is theta, times 2, let's put the 2 there, tan theta sec squared theta d theta. All right, I think we're getting somewhere. Now, I can see this is ringing bells for me because sec squared theta is the derivative of tan, so that's just a reverse chain rule there. So I'm going to use integration by parts and say let u equal 2 theta, because when I differentiate that I'm going to lose the theta. And then I'm going to say v dashed is equal to tan theta sec squared theta, and the integral of that, or the primitive function, is going to be tan theta all squared on 2. All right, up here, equals u times v, so 2 theta times tan squared theta on 2. Is that right? Yep. Between 0 and pi on 4, minus the integral between 0 and pi on 4 of 2 tan squared theta on 2 d theta equals, cancel, we've got pi on 4 tan squared pi on 4, take away, when I substitute this 0 in here, I'm going to get 0, take away the integral between 0 and pi on 4 of tan squared theta d theta. This question just goes on and on, doesn't it? Which is equal to pi on 4, take away the integral between 0 and pi on 4. Now, instead of tan squared theta, remember that tan squared theta plus 1 is equal to sec squared theta. So I'm going to replace this with sec squared theta, take away 1 d theta, which is equal to pi on 4, take away, and the integral of sec squared theta is tan theta, take away theta between 0 and pi on 4 equals pi on 4, take away tan pi on 4, take pi on 4, take 0, which is equal to, what do we got here? Pi on 4 plus pi on 4 is pi on 2, take away tan of pi on 4, which is 1, which is the answer. 15D, the complex number z satisfies this. Using the triangle inequality, or otherwise show that mod z is less than or equal to root 5 plus 1. Okay, here's our triangle inequality. Modulus of a plus b is less than or equal to the modulus of a plus the modulus of b. Now notice how we don't have a plus here, we've got a minus. So I'm going to make that a, and b is going to be 4 on z, like this. So z take 4 on z plus 4 on z will be less than or equal to mod z minus 4 on z plus modulus of 4 on z. So this is mod z here, less than or equal to, this is equal to 2, because it says it there, plus modulus of 4 is 4 on z. Multiplying everything by mod z, which we can do because it's positive, we have modulus of z squared less than or equal to 2 mod z plus 4, and then taking it all over the other side, we have a quadratic less than or equal to 0. Now let's consider the equality here, so I'm just going to solve using the quadratic formula. Will equal 2 plus or minus the square root of b squared minus 4 times a times c all over 2a, which is 2 plus or minus the square root of 20 over 2, which is, square root of 20 is 2 root 5, so this is 1 plus or minus root 5, which means that mod z take away 1 plus root 5 multiplied by mod z take away 1 minus root 5 is going to be less than or equal to 0. And if we have a quick look here, we've got 0 there, we've got 1 minus root 5 here, and 1 plus root 5. And I'm drawing in our little quadratic here. What do we want? We want it less than or equal to 0. So it is going to be less than or equal to root 5 plus 1, because it can't go past the 0 anyway. So there's our answer. 16a. A square in the Argand plane has these vertices, and the complex numbers ZA, ZB, and ZC lie on the square and form the vertices of an equilateral triangle, as shown in the diagram. So this is 60 degrees. Find the exact value of the complex number ZB. So we'll start off by giving some coordinates to ZB and ZC. I'm going to call this one B plus 5i, and this one will be C minus 5i. Now what we're going to do here is form these vectors here and this one, and then when I multiply it by a unit vector of angle pi on 3, I'm going to be able to make an equation. All right, so let's start off by forming x, vector x, which is going to be ZB minus ZA, which is B plus 5i minus 5 minus I, which is B minus 5 plus 4i. And then vector y is going to be, I want to go that way, ZC minus ZA, which is C minus 5i minus 5 minus I, which is C minus 5 minus 6i. All right, so here's the thing. Vector x multiplied by e to the I pi on 3 is going to equal vector y. Okay, this is a rotator in an anti-clockwise direction. You must have a magnitude of 1, otherwise you're going to change the length. Now x is b minus 5 plus 4i. E to the I pi theta, let's have a look at what that is. That's going to be cos pi theta, which is 1/2, plus I sine pi theta, which is root 3 on 2. And that's going to be equal to c minus 5 minus 6i. All right, expanding. I'm going to link these together. B minus 5 over 2 plus I root 3 over 2b minus 5 plus 2i minus, what is that? 2 root 3, I think, is equal to c minus 5 minus 6i. Now we're going to equate the imaginary parts, because that's going to eliminate c. Can you see that? So I have got I root 3 on 2b minus 5 plus 2i, I don't need the i's in there, is equal to minus 6. And solving, we are going to get root 3b on 2 minus 5 root 3 on 2 is equal to negative 8. Root 3b on 2 is equal to negative 8 plus 5 root 3 on 2, multiplying everything by 2. Root 3b is equal to negative 16 plus 5 root 3, and dividing by root 3, b is equal to negative 16 on root 3 plus 5. Therefore, ZB is going to be equal to negative 16 on root 3 plus 5 plus 5i. 16b, a projectile of mass m kilograms is launched vertically upwards from a horizontal plane with initial speed v0, which is less than 100 meters per second. The projectile experiences a resistive force, which has a magnitude of 0.1 mv newtons. V is the speed of the particle. Acceleration due to gravity is 10 meters per second squared, so we're going to have mg. Projectile lands on the horizontal plane 7 seconds after launch. Find the value of v0 correct to 1 decimal place. All right, so we start as always with F is equal to ma. In this case, m is capital M. And it's going to be equal to negative 0.1 mv, take away mg. So dividing through by m, we get A is equal to negative 0.1 v minus g. Now we want to know and get an equation in terms of time, so I'm going to use dv dt is equal to negative. I'm going to factorise this negative out. Flip it over to solve the differential equation. We get negative 1 on 0.1v plus g. Therefore, t is equal to negative integral of dv on 0.1v plus g is equal to negative ln 0.1v plus g all over 0.1 plus c. Now, at t is equal to 0, v is equal to v naught, so we end up with 0 is equal to v naught. So c is going to be equal to, I'm going to take that up there, positive 10 ln 0.1 v naught plus g. Therefore, t is equal to negative 10 ln 0.1 v plus g plus 10 ln 0.1 v naught plus g, which is equal to 10 ln 0.1 v naught plus g all over 0.1 v plus g. Now I want to make v the subject so that I can integrate it again. So I'm going to do something tricky here. Let's do negative t on 10 is equal to ln, and I'm going to lift that 0.1 v up the top. Hopefully that makes sense. And this is going to be e to the negative t on 10 is equal to 0.1 v plus g over 0.1 v naught plus g. And up here that's going to give us 0.1 v naught plus g multiplied by e to the negative t on 10 is equal to 0.1 v plus g. So 0.1 v is equal to 0.1 v naught plus g e to the negative t on 10 minus g, and then dividing by, well, let's just multiply by 10. So v will equal 10, 0.1 v naught plus g e to the negative t on 10, take 10 g. All right, now we're going to have dx dt is equal to all of this and so x is going to be equal to 10 integral 0.1 v naught plus g, that's all a constant there, e to the negative t on 10, take 10 g dt equals 10 0.1 v naught plus g, and I've got e to the negative t on 10 divided by negative 1 on 10 minus 10 gt plus c. Tidying it up, we get negative 100, 0.1 v naught plus g, e to the negative t on 10 minus 10 gt plus c. At x is equal to 0, or at t equals 0, x is equal to 0. Substituting in, we're going to get c is equal to 100, 0.1 v naught plus g times e to the naught, which is 1. So x is equal to negative 100, 0.1 v naught plus g, e to the negative t on 10 minus 10 gt plus 100, 0.1 v naught plus g. All right, when t is equal to 7, x is equal to 0. So 0 is equal to negative 100, 0.1 v naught plus g, e to the negative 7/10, 0.7, minus 10 g times 7 plus 100, 0.1 v naught plus g. And that's equal to, let's expand this out, 100 times 0.1 is 10, so negative 10 v naught e to the negative 0.7 minus 100 g e to the negative 0.7 minus 70 g plus 10 v naught plus 100 g. Okay, let's collect those v naughts together. So we've got 10 v naught, and it will be negative e to the negative 0.7 plus 1 minus 100g e to the negative 0.7 minus 70g plus 100g plus 30g. Okay, and taking these two terms over the other side, I'm going to end up with 100g e to the negative 0.7 minus 30g is equal to 10 v naught 1 minus e to the negative 0.7. And now finally making v naught the subject, v naught will be equal to 100 g e to the negative 0.7 minus 30g all over 10 brackets 1 minus e to the negative 0.7. And substituting in g is 10, we get 1000 e to the negative 0.7 minus 300 all over 10 1 minus e to the negative 0.7. And we put that in the calculator, we end up with 39.05 meters per second. 16c, it is given for positive numbers x, 1 through xn with arithmetic mean a, that this is true. Suppose a rectangular prism has dimensions a, b and c and surface area s. Show this inequality. Now, of course, this is the AMGM inequality, which says that the geometric mean is always going to be less than or equal to the arithmetic mean. You can get it from this, but I always just remember it. Geometric mean is always less than or equal to the arithmetic mean. Now, in this case, we're going to have 3 parts, so we want, say, the square root of x, so cube root of x, y, z is always going to be less than or equal to x plus y plus z all over 3. Okay, so we're going to figure out what to make x, y, and z. Now we know the surface area of a rectangular prism with dimensions a, b, and c is going to be 2 lots of ab plus ac plus bc. So I'm inclined to let x equal ab and y equal ac and z equal bc, which is going to give us this, the cube root of a squared b squared c squared. It's going to be less than or equal to AB plus AC plus BC all over 3. And this part here, that's equal to S on 2. So this is going to be ABC to the power of 3 halves is less than or equal to S on 2, so that's S on 6. And just raising both sides to the power of 2/3, we're going to end up with the inequality that we want. Part 2. Using part 1, show that when the rectangular prism with surface area S is a cube, it has maximum volume. So from part 1, we know V is going to be always less than or equal to S over 6, all to the power of 3 halves. Now the surface area, if A is equal to B is equal to C, is going to be 2 lots of A squared plus A squared plus A squared, which is 6A squared. And the maximum this volume can be is the equality here. And S is 6A squared divided by 6 to the power of 3 halves, which is A cubed, which happens, of course, when A is equal to B is equal to C. 16D, last question. Find all the complex numbers Z1, Z2, Z3 that satisfy the following 3 conditions simultaneously. Now, this is a really awful question, and part of the issue is that if you don't see the trick, then you can't get the answer. However, we can get 1 mark quite easily, and it's by using this here. So I'm going to start off by saying, well, let Z1 equal RE to the I alpha, let Z2 equal RE to the I beta, and Z3 equal RE to the I gamma. And now using this one here, multiplying them together, we get R cubed, E to the I alpha, E to the I beta, E to the I gamma, which is equal to 1. And I'm going to write that as 1 E to the I naught. And so we can see that R cubed is equal to 1, therefore R is equal to 1. 1 mark. And that's all very well. Now, how do we use these two here to be able to work out the complex numbers Z1, Z2, Z3. Do you know it's a matter of recognizing that this looks like the sum of the roots and the product of the roots. And if you don't see that, you're going to struggle a bit. So we've got Z1 plus Z2 plus Z3. The sum of the roots, if this is a cubic, so we've got AX cubed plus BX squared plus CX plus D is equal to 0. Sum of the roots is equal to minus B on A, which in this case, from this guy here, is going to be equal to 1. So we're going to say, well, A is going to be equal to 1, and in this case, B will equal negative 1. Now the product of the roots is minus B, see negative D on A, and it is also equal to 1. We know A is equal to 1, so D is going to equal negative 1. But we don't have this. Which of course is going to be equal to C on A, or A is 1. So we need to manufacture this. So how do we do that? Well, we're going to use the fact that the modulus of Z, all of these Z's, is equal to 1, which means that Z multiplied by its conjugate is equal to 1, and the conjugate will equal 1 over Z. All right, I'm going to take equation 2 and divide it by equation 3. So Z1 plus Z2 plus Z3 all over Z1, Z2, Z3 is equal to 1. And splitting it up, I end up with 1 over Z2, Z3 plus 1 over Z1, Z3 plus 1 over Z1, Z2 is equal to 1. Now I'm going to use this and rewrite it. So 1 on Z2 is the same as the conjugate of Z2. 1 on Z3 is the same as the conjugate of Z3. And this will be conjugate of Z1, conjugate of Z3, conjugate of Z1, conjugate of Z2 is equal to 1. Now we know that the product of conjugates, it's going to be the same as the conjugate of the products of the product. So I can make that line go all the way over the top. And we also know that the sum of the conjugates is going to be the same as the conjugate of the sums. Now these you learnt way back last year in term 4 when you were first studying complex numbers. Now this doesn't have an imaginary part. So the conjugate of this is actually going to be exactly the same as the thing itself, if that makes sense. Which is what we want. And so therefore C is equal to 1. And so our cubic equation is x cubed minus x squared plus x minus 1 equals 0. Factorize the first two and the last two, and we get x squared plus 1 in brackets x minus 1 is equal to 0. And so x is equal to plus or minus I and 1, which is the values of the complex numbers Z1, Z2, and Z3.